So here are some material. So if we have nanoparticle, for example, of silica or glass, can we see this behavior? Even 5 nanometer, 10 nanometer? Why? Sorry? No, it's so small. Even a gold particle of 100 nanometer can show that. Even a gold particle of 1 nanometer can show that. We call it quantum dot. So why we cannot see if we have a dielectric material? Because the condition that I show you. The condition is this one. You have real part of dielectric function negative. If it is negative, you can see this behavior. If it's positive, you can never see that even if you go 1 nanometer. This is the simple reason that we have to fulfill Froelich condition, right? So we have different material. You can see the silica, they can't show, but with metallic or semiconducting material, we can see this behavior. Mostly, we can see this behavior easily with metallic nanoparticle like gold and silver, or aluminum, or some other material. But when we go for metallic to semiconducting, you know we have some band, okay? And that band is small in semiconducting, but in dielectric material is so big. So it's difficult for us to show this localized behavior in silica nanoparticle or some other kind of dielectric material. So there are different properties of this behavior that is localized plasma resonance. Scattering, they show scattering and they show absorption. So how we can understand this impact that nanoparticles show us scattering or absorption behavior? Imagine that this is a particle and light is interacting. So what it can do that? Either it absorb or it can scatter. Only two possibilities. So based on these two possibilities, you can get a lot of application based on industry. For example, my iPhone, sorry, I forgot on home. It has small 10 nanometer particle that are based on silver. So they are using this kind of behavior. In modern car, they use nanoparticle to absorb energy as a nanofluid. So it has a lot of application now, and nanotechnology industry is growing day by day based on these features, either absorb or scatter. So how we can find this signal? Either we have wave shift, wavelength shift, either we have field enhancement, or either if we have some kind of dark spectroscopy, we have a change in color. You see that the color changing. So it's because of localized surface plasma resonance behavior. Come on. Okay. So here we have nanofluid. What is nanofluid? Simply you have nanoparticle. You can insert in fluid like water, acetone, oil, and we call them nanofluid. So basically these are nanoparticles. If you haven't covered, you call it nanoparticle, but in industrial level, if you have, in water, same thing, you call it nanofluid. So why we need nanofluid? It's simple experiment. When we have summer, we put a water, open air, we see that evaporated, right? So imagine that you have winter and you put the water, but it's not quickly evaporating in case of summer. What is the reason? So if you put nanoparticle, what they do that? Water will be heat up so quickly. Especially in Brazil, we have a long ocean, So there is a very hard to get fresh water. So normally what we do that, we have some kind of desk, we call it direct absorber collector, solar collector. We use water, that is a salty water, unable to drink that. And when the solar light interact with the nanoparticle, nanoparticle thermalize the surrounding. So water heat up. So when water heat up, what happened? Evaporation. So we have some kind of roof and water stick there, and then it come like that. So you can easily get a clean water using this technique. So this is the major application normally where we have a big ocean and we have a problem of water, underground water that is salty or ocean water is salty. So we have particle light, solar light interact, not laser. This is different. So solar light interact, they observe, and they change this energy, absorption energy, into thermal. So we say it thermalized, the surrounding, okay? And you see that. In this way, they heat up the water and change into evaporation to clean the water. So here is a graph. You can see the big difference. We have a graph, and you see with the help of nanoparticle, the optimized nanoparticle we can easily reach within 400, about 140 Celsius in 400 seconds. So it means they are very quick. So here are two ways to detect the behavior. Either they are showing absorption or scattering. So here we can calculate or we can evaluate absorption, and here we calculate scattering because our detector is at the angle. So absorption or transmission and scattering using this kind of spectroscopy. It's easy, you can even make in your lab. So here we have a different kind of material. You see 0-dimensional, 1-dimensional, 2-dimensional, 3-dimensional, metallic and non-metallic. So what is the advantage of metallic? Because as they observe, they totally use this energy to heat up the surrounding. Yeah, and here is little less because they have losses and other defects that cannot, all the energy they observe, they cannot change quickly into the heat. So in my research, I use only metallic nanoparticle or nitride, like titanium nitride. So I will show some of my results in next slide. So here, different kind of solar cell that we use, that we call it, one is the disk. This is a flat solar cell. So disk, you directly use solar light and you directly converting desalination process. You say that you have salty water and you changing it into clean water. And here is flat. So in my research, I basically work on disk. So this is the motivation actually for me when I start to work, because the person who hired me already publishing in that. But in our case, when we use a research, for example, when I was working in Sao Paulo, I realized that people are using a lot of gold nanoparticle, but they don't know which is the proper size, which is the proper shape, and which is the proper material. And this information is very, very important before you go for application. And you see that if you go on using gold nanoparticle, silver nanoparticle, you find a million of papers. But nobody optimized the system that they are using to develop their platform, either for sensing or for solar or something else. So this is the reason I started from calculations. So either they are environment friendly, this is also issue. Stability in nanofluid is very, very, because if we have gold and silver after 5 months, sir, yes or no, better than me. After 4 months, 5 months, they, agglomeration started. So it's very hard to use them as a nanofluid because you need, totally different, dispersed nanoparticle actually. So this is a big issue. And then the cost, because at industrial level, you always try to save money. This is the key. Optimization, okay, you are doing all and getting maximum efficiency. So this is the motivation for me when I started work with this kind of research. So particle stability is one of the key elements in nanofluid, especially when you are working with nanoparticle, any kind of nanoparticle, and if they are aggregating, they will give you nothing, or their performance will be very, very low. So this is the one of the parameter, and the second is particle size. if we are working gold nanoparticle, we know that gold nanoparticle wavelength spectrum shift is between 510 to 570 or 6, maximum that. But if we see the solar spectrum start from 350 and go to infrared, right? So 85% efficiency of solar spectrum, that solar we have, is around 350 to 1200 nanometer. So we try to make the spectrum as broad as possible to harvest from 350 to 1200. So this is the idea when we use it for photovoltaic solar cell, or we want to use it nanofluid, any kind of application. Here is shape, particle shape. If you see this, the efficiency depending on the shape. If we have just water, the maximum efficiency we get 13%. The thermal efficiency increase 33 if we have gold nanoparticle spherical shape. If we have triangle, we can get 65%. If we have some kind of cage, we get 21. If we have nanorod, we can increase 100. So this is a review that I published this year, actually, and it's published in 20 Impact Factor. I think if anybody want to do research in this field, he must read that, because it is everything. We follow all the review paper and we find their defects and we missing part, and then we include everything there. So material composition, another thing. If we are using gold are very active in nanofluid, okay? If we are using some semiconductor material, we didn't get too much efficiency, as I already discussed. So what is the application? We see satellite, right? We see car engine that heat up so quickly. So people use in car engine nanofluid, they absorb the heat, right? For desalination, we clean the water for drinking if the water is from ocean. For housing, many people use to make the kitchen water and the bath water room using nanofluid. So it has a lot of application. So here my research start. I don't know what happened with this research. Okay, so I published a paper in solar energy 4 or 5 years ago when I started this research. And as I told you, that the optimization and novelty of the material is very important. So this is a gold nanoparticle, you see. What we did, we just include 5% iron. We doped gold nanoparticle. And you see here effect. This is pure gold, the black spectrum. And you can see by adding 5 to 15%, the spectrum broader and the absorption is very high. With the simple trick, right? And this is a total theoretical work. This guy has a particle, he didn't give us, but if we have, we can go more higher impact factor. So you see that as we increasing the concentration, the scattering decreasing. As the scattering decreasing, absorption increase. And that is the motivation. In the next research, I use this. Actually, this research is collaborated with the American guys from Naval Office. So we win funding from them about 50,000, my boss. And the idea was to do something, about dimmer. And Sir Yasser, you know that the point is that if you combine two nanoparticles, you have two plasmonic peaks. One is in infrared and other is in visible or near infrared. So for solar application, we don't need that resonance that is in infrared, because maximum harvesting is between 400 to 1200. So what I did, I joined them with some kind of silica, right, or some polymer. And with joining, you remove that peak that is in infrared and you make broader this peak. So as we increasing this chain, you see that the absorption increasing and scattering decreasing. So this idea I published in 3 papers, a very good paper. In one applied thermal engineering, and the other is in IEEE, and one is I don't forget. And all is theoretical. And when I published in IEEE, after 1 year, that guy used same sample from Germany and he published in Nature Communication. Same idea. Because he has just experiment. If we get experiment, surely we go there. But the problem in pandemic, he didn't send us sample and they published in after 23. So here we use titanium nitride. Why we use titanium? This is a gold and this is a titanium. You see the difference? How broad is that? With the same size. We prepare this nanoparticle with laser ablation. Why? Because gold nanoparticle, as I told before, after 5 months, 6 months, aggregation start, agglomeration start. You cannot use them as a nanofluid. So we prepare with laser ablation, and the electronegativity of the particles go very down, -40, -30, and you can keep them like 5 years. And this kind of particle are very useful for industrial application instead of gold or silver or other things. Because you have a broad spectrum, and this is experimental. You see the temperature variation between gold of same size and with titanium nitride. So there is another idea in our group. This guy, Cardozo, he's working on perovskite solar cell. So what is the idea? You see, if we don't have particle, because the sheet is like X-ray sheet of perovskite solar cell, if you see that, all the light pass. So the efficiency is like 5%, 2%, 10%. And the perovskite efficiency maximum 22% that you can have out of 100. So it's very low already. So what we did, we used zinc oxide nanoparticle. Why zinc oxide? The question is that, not gold or silver, because they scatter more. And one of the projects that I work with, the Nanophore, as I told you, we have a project on a cream that we use solar protector. So the idea was that mostly cream, they can absorb more light. So we give them idea, okay, if we can use zinc oxide, some kind of this, they can more scatter than absorption, right? So this idea we apply also here. So here we use zinc oxide, and you can see zinc oxide playing 2 parts. One, it is absorbing. The second, it is scattering. So when it scatters, the light is absorbed by the sheet, and when it absorbs, it's already using that. So in that, we don't allow the solar light to transmit all. We try to keep as much as we can. And you see, here we get efficiency, some kind of, our nanoparticle is not good, so I don't want to show you, because this is not experiment is not good, but theoretically we get very good results. So we try to keep to show, experimental in that order. So here I'm talking, this is the second part, and I'm talking AI for innovations. So what is AI? When we talk about AI, artificial intelligence, what comes in your mind? You are a student, so if you give me answer, I will be eligible to understand how much you know about AI or machine learning. Anybody know that? No? How you define AI?
कंप्यूटर को इस काबिल बनाते हैं कि वो हमें इंफॉर्मेशन दे सके, इसलिए मॉडल बनाते हैं कि वो प्रेडिक्ट करके हमें आंसर दे सके अपनी, जो जिस तरह उसको ट्रेन किया जाता है, फिर वो अपनी जिस तरह में ट्रेन किया जाता है उसके साथ वो सोच के हमें हेल्प प्रोवाइड करते हैं। वैसे मॉडल यही है ना, चैटजीपीटी वगैरह कई मॉडल है कि उसको ट्रेन किया जाता है पहले डिफरेंट डेट के साथ, और उसके बाद जो भी उसको चीज़ दी जाती है वो अपने प्रेडिक्ट करता है पहले किसके साथ क्या आना चाहिए, फिर जो मोस्ट प्रेडिक्टेबल रिजल्ट होता है वो हमें प्रोवाइड करता है।
Okay, so one thing that I understand from all of your answer, first of all, thank you, is we get something quickly. That is the AI purpose. But the real definition, this is a definition I also wrote about here. But for AI, this is not the accurate definition. Okay, this is a definition, sorry, yes, that we use for computer students, okay? So AI can give you response based on the pattern. Imagine that you don't have pattern. You don't have input data. AI cannot help you. This is a simple definition. Mostly people define it wrong. They say AI can predict future. How can it predict future without, right? That came from past or present. So if I do this, what you get? You get sound. This is a response. Response of AI work like that. This is so simple, right? So there are millions of applications nowadays. Everywhere you can use AI. Even you can take an image of a person and put, and AI will tell you he is sick. If he's sick, which kind of disease he has. So it's totally revolution. You have car without driver, everything. So here are some major applications. One is biomedical engineering. And why it's major? Because I'm working in that these days with the hospital. So imagine that you have a tumor. Sorry, not you have. Somebody have tumor and you have an image, okay? You are doctor. So here you can see image. You can see the tumor, right? So what you see that? You see, okay, there's a tumor, but you don't see how deep it is. Can you see that? Of course not, because you have two-dimensional image. So it's impossible for you to define how deep it is. This is where you can use AI. It will not only tell you how deep, it will also tell you how big length or volume of that tumor is. Even you get 2D image. The second application, we have a big issue of pollution, especially in Pakistan. And there are different kind of size of particle, like PM10, PM2 particle matter size 2.5, below 1, 0.1. So if it's above 2.5, it's easily to digest. If the particle matter size is above, like gas particle or some oil particle, something like that, easily to digest. But if the size is below 2.5, it will stuck with kidney, it will not pass from there. And you see the kidney stone problem is growing day by day in Pakistan or India, something like where we have this pollution. So you can determine, you can use a ladder, and with the help of ladder, you can get a signal. You can use AI, okay, this environment has this kind of particle size, and how much concentration, you can easily define that. Another application in material, you can characterize your material. You can find the size, find the shape, find the defects inside the material. This is also very important. Mostly in battery, people are using this AI to increase the efficiency of batteries, lithium-ion battery especially. So what kind of information we need if we have to apply? So we need raw data, and data from comes anywhere, but we need data. As much as we have big data, we have good information and more good accuracy. As the data is small, if we have two figures, one is dog and cat, and we give AI, it will say, okay, dog is cat and cat is dog. So you need a good information to justify what you want. Otherwise, it's very difficult. Then you have to pre-process data. Especially hospital data, there are many missing values. Like if you are calculating blood pressure of a heart patient and you have a history of 5 years and there are some missing value. So you need to remove them, or you have to get average of the first value or the second and put there. Because if you have imputation problem, data cannot work. Machine learning will not work. Then you have to define feature and labels. And this is the most difficult task, because hospital data is blind data most of the time. You have image, okay. I give you 1 million image and I say, oh, I need, for example, one of my project, we are using blood cancer and we have to identify the subtypes. And the data is so big, sometimes my computer stuck with that. So you have to define before what is label and what are the feature to make it clear what you need there. Then you have to apply model. Any kind of model you can apply, you get something. If model is not working, you can replace. It's so easy. And then you can apply in a hospital and medicine designing something else. So basically, we have three types of machine learning that's working. One is supervised. Supervised, we have this class, and we know, okay, 12 are girls and 10 are students, male students. So we are classifying. We call this classification supervision. So this is a supervised machine learning. Unsupervised, you have blind data. Like you have a big basket and you have banana and other fruit, but you don't know how many, right? So this is a difficult task when we have unsupervised. This is a more hard task because if you are supervised, you can easily solve it. You know, okay, these are girls, these are boys, okay. What I have to find? The weight of each. And then reinforcement. This is more difficult type of machine learning because here you have agent. Suppose you are playing a game like we played several years ago, snake game. So if it's winning, it's going big and big and big. But if you are losing, we punished. Okay, what? We lost. Punishment is lost. So we have agent and we have environment. And both have to collaborate each other to get better results. Mostly movies data. If you have a get data, for example, I get data from hospital of bacteria, pneumonia bacteria, and it's based on a spectroscopy movie. So with this kind of data, it's very hard to get without reinforcement learning. So if we have supervised, unsupervised enforcement, what we have to do if we get? First, we have to do imputation scaling feature in all. There's no missing data. Then we have to define our model, and we have to train and validate, and then test. The key in machine learning is that if you are working with machine learning, and if your train and test data is mixing, you get underfitting and overfitting. It means your model give you wrong value. For example, if you go to bank, you put your ATM card in machine, and you see, you forget password, machine think you are fraud, right? It's simple. But it's you are there physically, just you forget the card. Okay? So this is so difficult sometimes if the machine think that the data is not so clean. So you have to think what is train and what is test and don't mix it. If you mix it, there is a big problem if the person know that you are working with him. The second is unsupervised. This is so simple because mostly unsupervised we do to use dimension reduction. For example, we have a feature of 1 million and we want to see 2 or 3 features. We can reduce it. So when we do reduction, what we get? We get most important feature. And the other feature, we say that these are outlier, unimportant. We remove them. Reinforcement, we need, first we think what is the reward, then the best action, and then we state and, okay, agent help us to win that if we are motivational and experienced. So in all these 3 different kind of things, we need clean data. If we don't have clean data, you don't work with anything. And mostly in biology, in medicines, where people like me suffer, we spend more time, like 3 weeks, 4 weeks, just to clean data. Even the cleaning, you think very simple, but it's so hard. When you have million of image or big data like 100 gigabyte, something like that. So there are different techniques. Here I give some example, like PSA, we reduce, regression, we regret, we have clustering. Imagine that you get the data from hospital, and hospital say, okay, this is the weight of the patient, and give us how many children, how many women, and how many male and old people. So you can see that if the weight is below 15 kg, you see that, okay, these are the children. Okay, if weight is 20 to 50 women, okay, weight is 50 to or 45 to 70, you say these are male. So this is called clustering. And then we have sport vector machine. So in these things where we are using each model, we have to define and label the data. So for example, if your data is continuous, you cannot, these both are machine learning, supervised. If your data is continuous, you can use only this one. You cannot use this. So this is the thing that you have to know before you go for AI or you have to apply something. So to predict a class, this is also difficult. You have different class, you have numerical output, then you have classification, you have dimension reduction, regression. Everything depends on the data and how you define the data. So in order, I met many guys and they say they know machine learning. And when I read their results, because I'm referee of many journals, so I get a paper from India last month before traveling to here. And the guy said they use machine learning for designing optical sensor. So sensor is my area, and because they use machine learning, it's also my area. And they show receiver operating characteristic. The value is about 60, 65, and they write that 93%. In the graph, so I said, I write that, how can you do that? It's so clear that you have a threshold line and the curve is close to threshold line, about 50%. How can you say it's 93, 0.93? So the point is that students think they are very smart, but sometimes they have bad day or bad time, so they get rejection. So here, different model, SVM, random forest, decision XGBoost, and blah, blah. You see that, what is the difference between each model? For example, this model is very good. You can superfine for big data. KNN is very small, is very good for small data. If you put this for big data, it takes a long time, and it gives you wrong results. And if you use this for small data, you again get overfitting, underfitting. So these are the problems when you have selecting. So let me define what is underfitting, good fitting, and overfitting. You have this data point, and the fitting line just pass, get minimum point intact. So this is underfitting. Good fitting, it goes smoothly, right? And overfitting, it connects every point. So these are the problems we have to take care. And when we have imbalanced data, then this is a big problem. Imbalance means 10 girls, 20 boys, okay? This is called imbalance. That if 10-10 is balanced. So balanced accuracy or imbalanced accuracy is very important. Mostly when people have imbalanced data, they use deep learning. So in this way, they define F-score or some other thing. But if they have balanced data, either first they balance it, or second thing what they do, they don't calculate accuracy. They go for F-score or some other kind of recall or other properties. Then train and validation, and test data should be unknown. You don't need to see the data, train data, you don't need to show your train with test. Don't mix it, otherwise you have this problem. Loss and training time. If your loss is small, your model is good. This is mostly used in deep learning. And here, imbalanced data. You see that we have some sample green and the big class B is big. So this is also a big problem. And here we have one hot encoding. And what is one hot encoding? That you have a car, you have a bus, and you have a truck. So you say car is 1, other 2 are 0. In the second, you say this is a car, the first one, the bus and truck is 0. So this is called one hot encoding. We use it when we have categorical data, category, right? And this is a continuous if you have color, because spectroscopy data comes from color. There is no water.
Yeah.
Oh, thank you. So before machine learning, people use this statistical analysis. Statistical analysis is mostly based on p-value. So if the p-value is less than 0.005, you define or 0.001 or 0.01. It depends which kind of application you are using. So you say there is a correlation between the variables. And if it's not, you say there's no correlation if it's bigger than that value. This is a statistic, but this if you imagine that you have a data of all the universe based on a patient who has diabetes. So it's a super big data. Then this is very hard to use that. Then you ultimately have to go to machine learning. So here we have a machine learning. So suppose that we have a patient and we have a healthy person. So we say that patient without disease, healthy person, true negative, and the patient true positive. Okay? So when these two curves overlap each other, you call it cutoff line. But if you see this curve part, this is a true positive. But we misunderstand that it's a part of true negative. So we have true positive and false negative. So important thing is here that this false negative is just like a man go and he do ultrasound and doctor say, oh, you are pregnant. So this is a more dangerous thing than a woman go and she is pregnant but doctor says you are not pregnant. So in machine learning, this error, false positive, they call it sometimes false positive rate. This is a very bad thing that we consider when we evaluate accuracy of some kind of decision. For example, I get an image of about all the 10 hospitals based on autism disease, brain disorder, and then I give you an example in future how this is very bad. And I discover, okay, my results are very fine, okay, this kid has this disease, this kid has this patient ID is this. But doctor say, no, they don't have. Or doctors say these patients have, but my model say no. So false positive is the decision maker in machine learning. Another chance to find that the performance model is this raw curve, receiver operating curve, characteristic curve. This is mostly used in radar from last century. See that if it's 50%, the curve is, we say the threshold. Now our model depends on these two decisions, either below 50% or above 50%. If below 50%, model is not working. If above, classifier is very good. So that paper that I'm talking, their curve is around this threshold line. And inside they write 0.93. I said, my God, how can this happen? And bad thing for them that they submit same paper in other journal and they send me again that paper. So I said, no, I can't do that. Two rejection from my side, they will abuse me a lot. So here we have imbalanced data. It's a data of fraud. You go bank and 99% you have accurate value and less than 1% you have fraud things. So if you give this data to machine learning, it will say accuracy is 99%, right? But in reality, it's not, because it's only counting these negative values, not this positive value. It's ignore that. So that's why imbalance data is very important when we are working with machine learning. So here is an example. We have patients in a hospital like 1,000 and sick is 70 number, okay? So you see that we have predictive positive, predicted negative, and actually positive, actual negative. Actual means the doctor says that. So suppose you have 40 people, they are true positive, they are really sick, okay? And you have 920 true negative. So there are 40 people, you have to decide either they are positive or they are negative, okay? So if the system say, okay, these 30 are false positive and these 10 are negative, and when you use a formula of accuracy, true positive plus true negative divided by all, okay, you get accuracy 96%. But when you get a precision, you get 57%. You know why? Because this factor. So accuracy you get super 96 is so high, close to 100%. It means model is perfect. Precision show model is not perfect. So it means there is something wrong with the model. So what you do, you calculate recall, specificity, and F-score. And see that F-score is 66%. So that's why people don't calculate accuracy when that is imbalanced in especially every field. Okay. So here is a paper that I published, and I was telling Sir Yasser about that I started this project 1 year ago. And last summer, when I started, it's on autism brain disorder. And I was lucky I published in, according to Chinese Q1, so quickly. And everybody is surprised. So the idea is that we have a patient, and this is functional near infrared spectroscope. You see, we have detector and receiver. Okay, we send the signal, the cells absorb this signal and they reflect back. Some brain cells absorb more, some less. So this is the thing that this FNIRS do that. So what happens when we have a normal brain and when we have ASD brain, the person who has autism? What is the difference? So our brain when we work, it's just like gun. Okay, it's fire. When it fire, you need bullet. Similarly, when our neuron, that's a billion in our brain, they fire, they need oxygen. So when they get oxygen, we call it oxygenation. And when the bullet finish, it's called deoxygenation. This is the simple idea. So the children that the autism, they don't respond quickly to this loading. So this is the point where you can detect, because you don't know 6 month or 1 year children or 2 year have. I remember when we were a kid, if we don't study, teacher used to slap, you know. So I still remember this period. So at that time, autism doesn't matter. But now in America, out of 4 children, 1 has this disease. So this is very severe disease. So the thing is that we use this research, we get 27 patients of 24 of ASD and 27 normal to compare them. And you know that's, here are the different shape of brain when they absorb oxygen and when they release oxygen, okay? So you see that. Here you get a lot of data because we have 41 channels, okay? And these channels give us thousands of values, okay? But I use p-value here, ANOVA. I use ANOVA, and with ANOVA I get only the significant features. Other I said, okay, outlier, I don't need that. And then I use clustering, and you see that the width of each channel is different from the other. So if the width is big, what it means? It means that channel responds better than this channel that have small. So with this comparison, we can detect, okay, this children has ASD and this children has no ASD. And also we found the true positive rate and false positive rate is very high, about 0.9. So here, how we can use machine learning in solar cell. Okay, we are working, as I told you before, and very big group in Chichang University. Still, we didn't have something, but this is some data. Imagine that this research is called data mining. So what is the idea of data mining? If Sir Yasser decide to do something on gold nanoparticle for optical sensor, so what he want to optimize, so no, it's not so difficult. What he do that? He write in Google, he will get 1 million abstract, okay, right? When he get 1 million abstract, so he can get the information on optical sense, like he said the refractive index sensitivity, okay? So when he sketch about out of 1 million paper, he will get like 2,000 paper. Other paper don't have this kind of information. So he don't need to read 1 million paper. He go only for 2,000. So this is called data mining. Like you mine and get a gold from, and you dig it, dig. It's so easy. And this paper published in Nature Energy and 4 years ago almost, and it's very high journal, 64 impact at that time. So they use this idea. They write perovskite solar cell. They want to define its efficiency, and they want to find which kind of material is better, which kind of configuration is better. So they get a lot of 50,000 abstract, and they realize that, okay, these abstract has efficiency, these have no efficiency. So in this way, they filter. So here is a paper that's also on machine learning using data mining. You see that there are a lot of image, and Professor Zishan used this kind of spectroscopy analysis in his research. And using this image, it's 1,000, he identified that this material is better and this material is not better. So in my first or last slide, I told you that if you want to find a defect or material composition, AI is perfect tool. You don't need to spend 2 years on your experiment. You first go find which proper composition is better or which configuration is better, and you go and handle that. And here you can find that the lifetime of a battery. You see that this is the actual and this is a predicted value. Even the value that he showed, R-square correlation value is very small here. You see 0.81 and here 0.58, 0.78. But still he succeeded to publish in Nature Communication. Because this is related to battery. And battery is a hot subject. Lithium-ion and no sodium-ion battery. So in this talk, I try to convince you that machine learning is a good thing. So if you have spectroscopy data or without spectroscopy data, go and hunt using machine learning. It saves your time. It makes you very hot person in the universe. Anybody can hire you, virtual job or other jobs. And you can easily get a scholarship, easily get postdoc scholarship, PhD scholarship if you publish a single paper with AI. Anything in physics, in chemistry, in economics, and other things. So at the end, I want to thank you all, I think. Yeah, thank you. And this is my official email and my personal email. And this is my voice chat. If anybody have voice chat, he can scan that and contact me if he has question further. Thank you very much.
It's an excellent talk.
Thank you very much.
Questions, students?
Sir, we are already, physics students, and we have many papers already being published by use of machine learning. So many of us are familiar with ROC curve and SVM model and KNN, etc. Earlier, you have mentioned that KNN model is good for small data,
Yeah.
and SVM is better for large data sets. Can you tell me exact number or any rough estimate how many measurements we require for that?
Okay, I can give you example. If Professor Yasser have to go as a candidate and want your vote in this class, he can easily ask you to vote him, okay? Because you are 50 around 30 people. But if he have to go for voting in a city of Faisalabad, it's very difficult for him to convince and talk to everyone, okay, vote me, vote me. KNN work like that. KNN go for every candidate, for every sample or candidate, and identify, and he say, okay, this is my voter, and this is not my voter. So imagine that if you have 1,000 persons, you can approach them. But in Faisalabad, I don't think there is 1,000 people are living, right? You have to go 80,000 people. So if you go this way, 80,000, your campaign till finish, the election finished before, right? So that's the reason KNN is not good for big data. Because it take a long time. That is a long consumption of time when you use your model. You don't want to spend 4 months and then you realize, oh, my accuracy is not good, let's start again. This is like that. Sport vector machine, if we have 50 people, it will do the same, right? It's like counselor and it's like MNA, something like that. So SVM like MNA and KNN is like counselor. So I hope I give you is any question more?
Sir, can you tell me please minimum number of measurements required for applying machine learning?
It depends on your sample, your input.
Okay, another question is that we don't know the basics of machine learning because we are physics students, but we are applying successfully by use of MATLAB statistical software. So can you suggest us any software with which we can apply?
let me tell you one thing. If you don't know Python, if you don't know our language, the life is difficult for you. You have to learn this language. Don't use MATLAB. Okay, this is a simple trick I'm telling you. In all industry, our language is using. In all academic research, Python is using. So either you should have to get a skill in Python, or in R. MATLAB is old-fashioned. It's like it cannot add the value. I'm sorry. I also used to work with MATLAB, the solar research that I show you, but I quickly switched to Python. Okay, so I think that's, if you have a skill in Python or R, even you publish or not publish, you have a job, virtual job, or you get a job in a good company. This is a simple trick.
Okay, thank you.
You're welcome. Any more?
Read with that.
थैंक यू सर फॉर योर नाइस टॉक. सर आपने कहा कि आपने ब्रेस्ट कैंसर पे काम किया है,
Breast cancer.
डायबिटीज पे, तो आपने उसमें हेल्दी और डिजीज पर्सन को कैसे क्लासिफाई किया, किस मॉडल की जो एक्यूरेसी थी वो बेस्ट थी?
Okay, again, a tricky question, but nice, very nice question. We get samples, from Argentina when I was in Brazil, 2022-23.
नंबर कितने सैंपल्स मिले आपको?
I didn't remember. I'm sorry, but there's no accurate figure at this time, because I switched too much, changed my area. So it doesn't depends that how many patients you have. I remember I don't have big number of patients in our case, because it's very hard to convince patient, especially in cancer. It's very hard to ask normal people. If I ask anybody, oh, I need something from, nobody will go and cut her, part of the body. So in experiment, if you are doing some kind of hospital, it's easy. But if you are working in lab, it's very difficult. For example, if you are working in a university and you need this sample, in 2 years, it's very hard. You collect 20 people. It's very difficult. And this is the reason that doctor don't help you in this, because I give you a small story that I working in Genoa, and there is a very good hospital. So my director took me there and he said, okay, let's collaborate. So that guy asked me, okay, I will not give you data. If you have to work, come here. So this is the problem. Because the data is, secret, patient don't want to share. Even if in China, if a father know his son has ASD, he don't tell anybody. So this is, I don't know what we call it, but this is very bad for researcher. So normally, I think you have to get at least 20 patients that they have breast cancer or skin cancer disease, and other normal as much as you can have. But normally it happens if you can get the data, most data come from patient and less data come from normal. So exact number, it doesn't matter, but the matter if your model is, for example, if you have a single video, like a pneumonia, I told you, pneumonia virus, bacteria, sorry. So it's enough, because you can sketch this whole video and get thousands of figures, 2D dimensional. And using this figure, you can, okay, this is train, this is test, and go on. But this one video is enough for reinforcement learning. Because in reinforcement learning, you have environment and agent. So environment is the body, agent is the bacteria. You can, oh, this is the bacteria, this is, so model will decide.
Yes, sir. ये तो फिर डीप लर्निंग में हमें जाना पड़ेगा अगर हम फिगर्स के साथ काम करेंगे.
Deep learning is a subset of supervised machine.
Yes, अगर सुपरवाइज में हम सिंपल ट्रेनिंग या एक्यूरेसी की बात करें टेस्टिंग में, तो मैंने ब्रेस्ट कैंसर पे काम किया नॉर्मलाइज के साथ, नॉर्मल पर्सन और कैंसरस पर्सन का मैंने एक्यूरेसी निकाली, तो उसमें मतलब ज़्यादा डाटा होगा तो एक्यूरेसी ज़्यादा अच्छी आएगी?
So now I can ask a question. So how you get this data? Because
How?
in now, yeah, how you analyze this data? You need the data in case of pattern. You use figure
Yes.
or you use spectrum.
We use spectrum, numerical value.
So which kind of device you use?
We use LIBS, laser induced breakdown spectroscopy. We record spectrum of each sample.
You get spectrum.
Yes.
In my case, I use FTIR
Okay.
or Raman, you know. And in this way, I use image and I convert this image into spectrum. So this way you get a lot of outlier. Unfortunately, I didn't put that. I don't know if anybody working. Sorry, next time when I come, I will show you. So if you have a big, like a wall, and you see my picture. So you see me here, just this is my part. Other is all background. So when we have spectrum, it's more difficult because we have more outliers. We need the information, only minor information, but we're getting all the information from background. We have no other way just to remove it. So it's just like that. So if you have spectrum, it's easy because already you know that. But if you have image, you have to clean it first.
सर मेरे डिफेंस में एक क्वेश्चन था कि अगर आपको ब्लड दिया जाए और आप बताएंगे कि ये डिजीज्ड है या हेल्दी पर्सन का है?
I cannot answer you because I'm AI guy, not doctor.
ओके, तो हम सिर्फ लिब्स जो हमारा स्पेक्ट्रम था हम उसकी बिना पे तो नहीं बता सकते कि ये कैंसरस है या नॉन कैंसरस है. देन वी अप्लाई मशीन लर्निंग फॉर क्लासिफिकेशन ऑफ कैंसरस एंड नॉन कैंसरस.
We have 1,000 of instrumentation that can tell us. We cannot see inside the body. For example, if you have a blood cancer patient, how you know that he has blood? You have to analyze by some kind of, with naked eye we cannot see if his blood generating white blood cell or not. We have to find that. We have to figure out that. AI simply assist based on that information that we input it. That is simple AI work. We give this information to doctor, then they have to decide. Okay, is it accurate or not accurate? Just we assist the doctor. That is our purpose. We assist the medicine maker. Okay, this way medicine is better. You know, this year the Nobel Prize win, the guy, he is younger than me, and he just protein docking, and he showed three-dimensional first time, and he get the Nobel Prize. So the thing is that we just help the people, you know, based on the information that we get from somewhere. Imagine that today is not raining. How do you know tomorrow is raining? So you need information based on today or yesterday or whole week history. So this is the way you can predict.
Still, it will be a prediction,
Yes.
Yeah,
not a final decision. So they will have to make a decision.
yeah. So this is not our work. This is the work, sir. We call it technical people, you know. And so you can simply ask, I'm not technical. So like me, I'm not technical. Okay?
Okay. Sir, one more question. We also use nanoparticles, silver nanoparticles and copper oxide nanoparticles for enhancing the signals. So, sir, nanoparticle size जो है वो कितना मैटर करता है गुड रिजल्ट्स के लिए किसी भी
है
टेक्निक में?
मार्कर वगैरह पड़ा हूँ.
ये तो है, वो है white board. अच्छा, उसके ऊपर ही आप वो
हाँ, इलेक्ट्रॉनिक बोल रहे. So आपका क्वेश्चन है कि
नैनोपार्टिकल का साइज जो है
how important nanoparticle size for sensing?
या
Okay.
maybe she's asking about light matter interaction. लेजर के साथ आप
Yes, sir.
ये देखिए. $10 nanometer and 100 nanometer. What do you think is more sensitive? Anybody else?
तो ये जवाब तो देना.
Don't worry, मैं मारूंगा नहीं.
No, sir.
आई
100
एम क्वाइट
nanometer.
फ्रेंडली पर्सन.
100.
100. आपने कहा 100.
Okay.
जितना स्मॉल पार्टिकल होगा उतनी
उतना-
स्कैटरिंग कम होगी. योर सिग्नल इज लाइक दैट. This is for 10 nanometer. For gold 100 is like that.
Sure.
It's very hard to do limit of detection. So how you do limit of detection? We have sensitivity and figure of merit. These are two very important parameters to predict if your sensor is good or bad. So we say eta B. Surrounding medium, you say is like water or some medium. Shift in wavelength, change in surrounding medium. This gives you sensitivity. Okay? Another parameter is figure of merit. That is how much sensitivity you have and what is the full width or maximum you have. Okay? So, which has bigger full width at how maximum? This one or this one?
10.
10 nanometer. They are reciprocal. As much as you have better figure of merit, you have this number very nice.
Okay.
This is the simple way to measure the sensibility of any kind of sensor. Either you are calculating chemical sensor or gas sensor or for disease, optical or non-optical. Okay?
Thank you, sir.
You are welcome. Any more?
Have you observed any limitations during your application of AI tools in your application? Any limitations have you observed?
And which kind of application, sir?
Limitations. And
No, I mean which kind of application, because every application has a different limitations.
because currently you have mentioned solar cell.
Yeah, solar cell. Can you elaborate your question so it's better for me to understand,
For
please?
example, you have applied for short circuit current because I have observed that short circuit current is increased, but not mentioned in the open circuit voltage.
So you want to know the limitations.
Yeah.
So the thing is that when we use perovskite solar cell, we have a lot of limitations.
Okay.
And the reason is that because it's low efficiency and its thickness. The other thing is that it is not so stable material. The thing we made with the perovskite solar cell. For example, if you talk about PV, photovoltaic cells,
Yeah.
you can use silicon. Silicon is so stable, even its efficiency is not so high. But why we use that? Because it's more stable. But in case of perovskite solar cell, the problem is the material composition. This is the one of the biggest material problem that we have when we do experimental in our case. Because suppose that you are working with zinc oxide or titanium particle. You want a bigger scattering, okay? Big scattering. But you need the exact structure that you design in your modeling. If your structure is not well defined, it's very hard to get the particular result. But experimentally, you cannot get spherical particle like that. Even you can try as hard as you might. But with gold, silver, titanium, you can easily get spherical nanoparticle or nano cage, something like that. So I think that's the big problem is the shape. The second problem is you cannot well define the thickness of that material that you are using as a perovskite solar cell. Because sometimes people use big thickness, so it even didn't, for example, this is your perovskite and you want to use a layer of gold here. When the light comes, reflect. So you have more reflection than absorption. So this is also a problem. So technically everything even you are working with any kind, the limitation is very important. And this is very fine question, because now people or reviewer ask, write the limitation of your work, where you can apply or where you cannot. So I think that's everything has limitations, especially in perovskite. You have material composition, size structure, the thickness of layer, because you are using a multi-layer. It's not a single layer. And then you have to match band gap, which band gap is proper, which is not.
And in your research, in how many applications you have applied this AI tool?
Okay, so I applied mostly in biomedical. Now we have a project on sodium-ion battery where we're supposed to use that. And I'm also looking for a sensing application to detect a single analyte. I mean a single disease molecule. Analyte, we say that, biological molecule. So that's the thing. Breast cancer, diabetes, ASD, and
Energy application.
energy application I didn't, because this work is old. Okay, it's my PhD and very starting work. So I changed later 3 years before in AI. So I'm not as expert, but I'm supposed to try, So this is the thing. So the thing is that we are working, for example, I'm working on a data mining now. It's a project on with the Tejo Hospital. And the idea is that how we can detect bacteria as quickly as possible. Because we have different sensor. So some take 2 days, some take 1 hour, so we have to give an estimation, which is a proper device and how much time it take to, detect that bacteria, any kind of bacteria. So it's in process, still not, we are in the line. So maybe next year we publish something on that. Any more, sir?
Thank you.
You're welcome.
Thank you, sir.
Sir, I have a question.
Yes, please.
And how we can apply machine learning on energy storage devices?
Battery is also energy storage device.
Sir, it's software we can use.
Software, I'm sorry, I didn't pick your question.
He wants to ask, what type of prediction we can do in energy materials like we are using? We can optimize doping percentages or.
Yes, she can do anything with machine learning. She can find the concentration in case of doping. She can find the lifetime energy storage device. She can predict, okay, this device can work 5 years or 10 years. Like we are doing in lithium or sodium-ion batteries, as I give some example. So you can do anything what you want. For example, the best way, if you have to start some project, I will give you idea to go for data mining. I design a model. So if I have 50,000 abstract or 20,000, I can find the proper parameter regarding efficiency, like lifetime, or some other parameter in 2 minutes. Imagine that 50,000 abstract. If you have to read it, how many days you will take that? So in just 2 minutes, I give all the abstract to my model, and it's make a table. Okay, this paper with DOI, with time when it published, who published, which parameter, it give me a complete table. So I think you should design some kind of this, and then you start your work, energy storage device. In this way, what you will get? You will get a better idea to optimize your system, which kind of system you are using. For example, if you have to make a device, you keep in mind that it's cost effective. It will give you cost effective with better efficiency. How many paper you can read? 5, 10, 12, and mostly people will read, they are inappropriate, not suitable, right? So it's a simple thing that you should start AI with data mining. It's more simple thing if you can go with AI. Otherwise, I know that's okay, for the sake of work, you can do that. But in this way, to get a position outside from country is very difficult. And my true suggestion to you is that everybody just start with data mining, download 50,000, 1 million, or how much abstract, try to build a model. And I think this model is enough for your defense, even for PhD, because you are dealing with big data. And big data is a proper field. Big data is quite proper field. No, I am working on a project, and my idea is to make a connection with ASD and Alzheimer's disease. So Alzheimer's disease happens when the people are above 60 years or 65 or 70, and ASD in the children. So I want to build a connection. It's a quite novel thing that I want to build a connection. If a children have ASD, how many chances in future he has that he will get Alzheimer's? You will never find any paper regarding that, I guarantee. So thing is that think something novel. Even it's published in bad journal, don't damn care. People think what you published. My first paper published in less than 1 impact factor, and is highly read on ResearchGate. Highly cited. All the journal send us congratulations, there's your paper. So thing is that people want to follow a good work. They don't damn care if you publish in Nature and this. That's it. So the thing is that you just think about what is the novelty. Anywhere you give an interview for a job, anywhere outside of Pakistan, because I don't have experience in Pakistan. In Pakistan, if you want to do a job, I don't know, sorry, yes, what he's supposed to do that. But the problem in other words, everybody will ask you what is the novelty of this work and the project. If you give him an answer, he will hire you. If not, even you have 100 paper, 1000 paper, he don't care. So this is so simple and technical way to go. And be smart, don't just waste your time like we did. Because I did that, so I know that. Just follow the things that make sense. Don't waste your time. In our Professor Yasser, in our period, we don't have ChatGPT. If you even know ChatGPT, you don't need any job. It has a lot of skills, a lot of implications. If you know better, no, you don't need job to earn here. You can earn $5,000 sitting in your home. So just try to make more impactful with the new things. Like my friend, he's working with still MATLAB. I'm quite surprised. In one way, you have to pay MATLAB. Python and R is free and more modern language. And I don't know, still people are using MATLAB. Maybe they feel relaxed because they don't want to suffer. This is the point. Yes, please.
Yes. सर मेरा क्वेश्चन है कि जैसे हम खुद एक स्टूडेंट्स हैं तो हमें एआई के बारे में इतना ज़्यादा तो नहीं पता, लेकिन पाइथन सीखने के लिए या डीप लर्निंग सीखने के लिए हमें किस चीज़ को फॉलो करना चाहिए, कहाँ से स्टार्ट करना चाहिए?
Okay, don't follow Indian or Pakistani. This is a simple trick I'm telling you. When I start to learn Python, I realized that it's quite boring. Even you want to learn, you run away. Try to read a book, either American author or European author. Try to get something from YouTube. The people, like this guy, he's very good in Python. His name is Mosh. He's very good. But the trick I'm telling you, even I buy his course. His course on YouTube is free, but I buy his course. It's quite boring. The thing is that you have to apply somewhere. Then you will learn. Many people don't know that. My nephew, he said that I know Python, but he didn't know how to. Implementation is more important than coding. Anybody can do code. Even if you like little kid 8th grade in China, he will do a better coding than me. But he don't know how to apply it. This is important. You have to, till you don't apply somewhere, you don't know anything. This is the simple thing.
एक last question.
जी जी.
That most of the students ask in the age of this computer and everything AI, is it still worthwhile to study physics? This is the major question that people
Okay.
ask before
So
getting-
I ask a question before them. Do you want me honest answer or hypocrite?
honest.
Don't do chemistry or physics something. No, there's no job. There is no job. So simple. My PhD in electrical engineering. Okay, there are jobs for electrical engineer, but the thing is that there is no job in physics, chemistry. I'm sorry, I don't want to disappoint you, but because you said that the honest opinion, so honest opinion is that AI is the future. Robotic is the future. Next war will fight by the robot, not by people. You see, 3-4 days India sent drone. What is drone? It's a robot. You have to get a skill now with AI. Okay, if this, I don't know how to make a shape of missile, but I try something, I don't know, but okay. Anybody can draw something, drone or missile. I'm not good in this. Okay, so suppose this is a missile. I don't know, it's okay, something, and it's a cruise missile that you are controlling from behind, and it detects its own target. You are sitting here in Pakistan. This is India is coming to here. So the next fight will be, next war will be start by computer, by AI. You have to break this code. You have to break this code. You know that recently in Ukrainian, they destroyed 7 billion nuclear airplane of Russia. They use drone, right? So this next generation is totally on AI. You don't need driver. You don't need skilled people in factories. Everybody jobless. But the person who know AI, he know how to control a robot. Because to control a robot, there is some mind behind that. Okay? So this is the point. In future, there's no jobs in physics, in chemistry, and other things. Only job that you can get, you need skill. And skill comes with AI and machine learning. This is a simple and most calculated thing. Even if you can apply AI, and one time I was in a seminar, a guy from Canada, he came, and he used AI and photonics, and so impressive. He published in like Nature Communication, a big journal, more than big journal. So the thing, if you know there is a problem, what is the problem? In our research, what I did, and maybe you are doing or some other people are doing, we produce problems. We produce problem, but problem is in front of us, like coronavirus. This is a problem. So what you have to design, or you have to make a vaccine. So research is, you have problem, you have to find a solution. This is not your imaginary that, okay, I can go moon by stairs. It's difficult. I mean that you are developing your own problem. It's useless. The problems are around you. You see that what is the traffic model in Faisalabad, for example. You can take all the data and you can use, okay, at 11 a.m., before 9 and 11 a.m., there's huge traffic from Monday to Friday. Okay, on Saturday, Sunday is free. So you have problem, but you have to give a solution to the people. This is the research, actually, according to me. I don't know other people think what. This is a simple thing that you have problem, you have to find the solution. Don't develop your problem that don't exist. Like magnetic monopole. Okay, everybody accept there exists, but there's no experiment. Einstein win Nobel Prize, right? Which application he win Nobel Prize? Exactly. But theory of relativity, we accept that there is theory of relativity. He didn't win because he didn't prove that. This is a simple thing. So the guy who win Nobel Prize, no, he is not experimental guy. He's theoretical guy. Because already people know that they need to see a protein interaction with the analyte in 3 dimensions. That is a very big task, and it solves this problem. Many people are trying from many years, but they don't, and he succeeded to do that. So this is the simple thing that we have to think. We are using material, we are using chemistry, anything you should connect with AI. Because in China, mostly industry, one of my students from Zhejiang University, he get a job before finishing his PhD. And still his PhD didn't finish. He got a job last year because he know AI. And trust me, he's very bad in AI. We submitted 2 papers, still didn't. And his salary double than mine. Even I have a big experience, that's, but he start finishing PhD, he is there. So this is the way that you can apply in physics and chemistry and material everywhere, but AI. Without AI, it's very difficult. Life is very difficult.
So we can say that it's not. It doesn't mean that physics and chemistry are not important, but they alone are not important.
You can,
because if you want to, you have to do AI with that.
Yeah,
with that with AI.
So we can say that coding is essential.
Yes.
If you are
no, coding
AI
is not. Coding is
we
not.
can't
AI.
survive without coding.
The people who do coding, they don't know anything. जी
असल में वो यही कह रहे हैं कि उसको लिंक किए बगैर फायदा नहीं है फिजिक्स सब्जेक्ट्स are one लेकिन
anything
AI के बगैर
anything you can use, but you can apply their AI. This is the purpose of talk. Okay, if you are not using AI, this is very hard for you to convince other. For example, we have a postdoc. So my boss is very strong. He is a professor in Sweden, and he is also a distinguished professor at Chichang University. That is on top 50. So normally in postdoc China, life age is 35, but we hire even above 40. But he wants people who know AI and medicine. This is the point. Okay, so before 35 you can get postdoc there, but after 35 it's very hard. But if you know AI and medicine, just contact me. I will help you to find the postdoc. It's so simple.
So thank you very much for a very nice talk.
Thank you.